So I wanted to make a series of video about graph and graph algorithm with Python and NetworkX because I think in CS graph are structured data structures that are very useful to represent relationship between data, and graph is heavily used in, for example, social network roadmap to find the shortest path between two cities, and also it is used in GPS to represent location. So graph is one of those structures that is very useful to know and to learn for representing data. So that's why we're going to use Python and NetworkX, which is a Python library that is very useful to represent graph in Python. So I'm assuming that you got everything set up because I'm using here, as you can see, Jupyter Notebook, and I already have this Python library already installed. But if you want to install them, you can just open your terminal and just type pip install numpy NetworkX and matplotlib, and you will get it all the to install. And before going further in some example, I'm gonna make sure that we understand some terminology about graph and what exactly is a graph. So let's get to it. What are graphs? So basically, graphs are structures that are made up with certain number of vertices or nodes, if you prefer, connected each other by edge or arc, depending on the type of graph. For a graph G, we can say that is a pair of edges and node connected together. So basically, in mathematical terms, graphs are noted like here, where like G here is representing the graph here, and V is the list of vertices or nodes. As you can notice here, we use sometimes vertices or nodes because in some textbook you can see vertices and other nodes, so it is important to use to understand those two interchangeably so you can not get confused when you see nodes in other book and some other vertices. And E does represent the list of edges, like the relation between those nodes. Depending on the graph, we can have edges, or sometimes if the graph is directed, we have axes. So as you can see, for a graph G, we have a list of nodes from V1 to Vn, and the list of edges to En, whereas a graph is just a pair that represents link between two nodes. As you can see here, basically we can say this is a graph because we have a bunch of nodes like here. Let me show you. This one is a node, this one. So basically all the numbers that you can see are nodes, and we can see that there is a connection between those nodes, like here, and here. So basically, as you can see, like I assume that most people are familiar with this because sometimes you can see it in a representation of road maps or subway roads. So this is basically a graph. Another thing that can represent a graph is also this. As you can see, we have a bunch of vertices not connected together by edge, as you can see here. So this is also can be represented as a graph. Also, this here is also a graph, but as you can see, there is a difference between the relationship here and here, because this is a directory graph with axes. So we have two type of graph. One that is undirected, like here there is no direction here, so this is bidirectional. We can go from this node to this node and vice versa, from this one to that one. But here the graph is directed, so we can go to node 1 to node 6, but we cannot go to node 6 to node 1. Like I explained it, as you can see, we have two type of graph here. Indirect graph where edge have no direction, which means that the connection is bidirectional. We can go from node A to B and from B to A. And direct graph where edge have direction, meaning that the connection can be between two nodes is one way. It does not necessarily mean that they are connected in both ways. So another terminology to understand about graph is a degree of a node. The degree of a node refers to the number of edges that are connected to that node. If the degree is high, it usually means that the node is quite complex or that the node is important. So usually we represent a degree of a node by this, where the node represents the current node that we are referring to, and a number representing the number of connections that the node has. So as we can see here, we have a graph with 5 nodes, 5 vertices connected each other by edge. And as you can see, for the node 1, node 1 have 1, 2, 3 connections. So the degree of node 1 is 3, as you can see here. And the degree of node 2 is 1, because node 2 have only 1 connection. And the degree of node 2 is 1, 2, 3, 4 connection. And the degree of node 4 is 3, and the degree of node 5 is 3 also. So that is basically the degree of a node. It just represent the number of connections that the node has. Another terminology to understand is clustering in a graph. Basically, clustering allows us to know in a graph what are the most important vertices, like what are the nodes that we can find the most connection, where the nodes are grouped the most. As you can see for this graph, we can assume that node 3 is basically the most important graph because he has more connection, but usually that's not always the case. Like the node that has most connection doesn't automatically mean that it is the most important node, so keep that in mind. For representing a graph in an algorithm, usually we use two data structures to represent a graph, because obviously we cannot represent a graph like this, so we need to transform it in the way that we can use different algorithms. So mostly when representing a graph in an algorithm, we use two data types like matrices and dictionaries. So for matrices, we can use a matrix to represent a graph, and in that matrix the row and the column represent the vertices, the node, and the intersection between a row X and a column X is the connection, is representing the edge, the intersection. And obviously the size of that matrix depends in the number of nodes that the graph has. And for a dictionary, we can use basically a entry representing the node and a list value representing the connection that the node has. So let's go into our notebook to see how we can represent a graph using NetworkX. So if you got these three libraries installed, you should be good to go. So let us run our set. As you can see, there is no error. So if you see an error, that means like you didn't have this library, or you make a mistake by importing them, so make sure that everything is okay. So using NetworkX to represent a graph. So first of all, we just need to create our object that's going to represent our graph. So let's create that object. Let's call it graph object. So let's call it G is equal to nx dot graph. So this is going to create our graph object, and the now G has all the properties that a graph can have, like node and edges. So let's go and add our node and edges. So let's just make a list of nodes. So maybe 1, 2, 3, oh my god, there is a list of nodes, so we need to add a list of edges. But remember that edge represents a connection between two nodes, so an edge must be a pair of two nodes. So let's connect our nodes. Okay, and just make sure that we can see the connection. That's one, and so as you can see, we have a graph object here. We have a list of nodes, and we have here a list of edges, as you can see. So we need to add these to our graph, and we can just call a function to add it to a graph. Call function to add to our graph. So let's call the function add node from our list of nodes, and there's another function add edges that we can use to add our list of edges. So basically around here we have our graph here with our node and the edge connection between those nodes, and we can just now represent it by drawing it. So we can use NetworkX for that, NX, to draw our graph here, G, and with labels. Sure. So if we run this cell here, we should see a representation of our graph. So let's run it. So as you can see, this is our graph here. You can see the connection here, and we can see our nodes. And obviously maybe this is not the representation that you got, because if I run it multiple times, Wave will not have the same representation. The only thing that matters is the connection between the nodes. That's the way to identify if we have the same graph. Because if I run it again, see, we got a different representation. So to see if two graphs are the same, don't focus on the representation. Just look at the connection between the nodes to see that if those two graphs are the same. So let's, for example, just add another node into our graph. So let's add a node 6. We can call a function add node 6, as you can see, and let's just draw, or we can just do it right here. So this will add a node number 6, but as you can see, node number 6 doesn't have any connection. So there's as you can see, there should be no connection in node 6. As you can see, node 6 is right here without any connection with the other nodes. So let's add some connection for node number 6. So we can just use the function add edge. Here we're gonna make connection between node number 5 and node number 6, and another connection between edge number 1 and edge number 6. So let us just draw our graph again. Oh my bad, I made a mistake. So let's just add edges. So let's run it again. As you can see here now, node number 6 is connected with node number 1 and node number 5. So we can also list the edge that are connected with a function called connected component. So get list of connected component. So there is a function called connected component, and we pass in argument or graph to get the list of connected component. Oh, I forgot, he returned a set of nodes. So let's just maybe sort that. Let's generate a list of sorted component. As you can see that all the nodes 1 to 6 are connected. So there's a list of connected nodes. So obviously, if you want to learn more about this function that I use, you can just go to NetworkX.org to get more information about this function and how to use it. So there is a list of connected components. Obviously, if we just add another node, add node number 7, and we draw our graph again. No, we don't need to, we can just generate a list of connected components. But since node number 7 doesn't have any connection, it should be isolated. So let's run our cell. As you can see, number 7 doesn't have any connection, so it is isolated. So basically, this is how we create a graph and network. This is one way to create a graph, let's say that. But as you can see, it is kind of tedious to list a graph, add node one by one, add edge connection one by one. There is another easy way to define your graph, so let me show you. So rather than adding graph line by line or node by node or edge by edges, we can just give a representation of our graph, like I said, in a data structure like a matrix or a dictionary. So let's do that. So rather than typing, let me just paste the code, and after I'm going to explain. So as like I said earlier, we can represent a graph by using a list of dictionary, a dictionary list. As you can hear right here, we have a dictionary that got 1, 2, 3, 4, 5 entry that represent our node, and we have a list that represent the connection that the node have. So for example, node A is connected with node B and C, node B is connected with node A, C and D, and node C, node D, node E, and node F, as you can see. So as we done earlier, we just create a graph object here called graph here, and basically to create a graph we just need to traverse this dictionary. So we just made a for loop for every entry, every node in that dictionary. We just added it into a graph object here, and for every list in that entry we just add those edges here. So basically at the end we can just display our graph here. So let me just, this is right here just for making the visualization more easy. So basically that's it. So let's just run our cells. As you can see, we have node A connected with B and C, node B connected with A, C and D. As you can see, node E connected with C, D and F. So that's basically the easiest way to create your graph, by using a dictionary of lists to represent our graph, and using the function add node and add edge to create your graph. So basically this is our graph. Oh, and I forgot to mention this function right here. Basically, if you have a object graph, you can generate a dictionary of lists for that graph. Basically that is exactly what we do here. So that is the output of our graph here in form of a dictionary of lists. Basically we can do the same with our graph G here. So let's just do the same here. Just copy, add it, replace it by G, and as we can see we got the same here, a dictionary of lists with this representing our node, and this right here representing the connection that the node had. So that is what this function does. So another thing we mentioned about graph is degree of a node. So there is a function that we can use to determine the degree of a node. So let's just display the degree of our graph G here. So display degree value for each node. So in NetworkX there is a function called degree, and in argument we pass our graph G. As you can see, it's written a dictionary of each node with the degree. So as you can see, node 1 got 4 connection. As you can see, it's connection to node number 2, 3, 5 and 6. Node 2 got 2 connections, so on and so on. As you can see, node 7 got 0 connection. So that's it. That is basically a way to view each node degree. Also, we talking about clustering, which usually use it to see what are the most important nodes in a graph. So as you can imagine, there is a function in NetworkX that we can use to calculate the clustering of each node, to view which node is is better connected, at the better position. So let's just do clustering. So there is a function in NetworkX called clustering that we can call with argument our graph object. And as you can see, there is a dictionary of our node and the cluster value. So as you can see, node number 2 and node number 6 are the most let's say valuable node. So they are the one that are better connected. So as you can see here, even though node number 2 and node number 6, they does not have the highest degree here, because node number 3 has 3 connection. But as you can see, for the clustering, the node number 2 and node number 6 are the best node are there. One last thing that I have mentioned is the ability to represent a graph by using a matrix. There is a function in NetworkX that can do that to show your graph representation in a matrix. So let's just representation with matrix. Matrix. Okay, there is a function in NetworkX called to numpy matrix, and we give a graph g an argument, and if we run it, there is no function to numpy matrix. It's kind of weird. Oh, my bad. The function is called to numpy array, I think so. Yeah, my bad. So as you can see, this is a representation of our matrix, of our graph in form of matrix, and basically each row and column represent our node. So here we have node 1, node 2, node 3, node 4, node 5, node 6, node 7, and the intersection between the nodes represent a connection. If it is the one, that means that those two nodes are connected. For example, if you have this one and this one, it means like node number 2 is connected to node number 1. As you can see here, node number 2, node number 1, so and so on. So that is usually how graphs are represented in a matrix. So that's it. Basically, that is all I wanted to talk about in part 1. So we talked about NetworkX, how to represent a graph. We talk about different terminology like degree and clustering. So that is all I wanted to talk about in part 1. In part 2, we're going to talk about more about graph algorithm like BFS, DFF, Dijkstra algorithm, and so on. So that's it. So thank you for watching. Please like and subscribe and write some comment. Thank you.